Good morning, good afternoon, and welcome to this Chemspeed webinar. My name is Chris Dietrich. I'm a Director of Business Development here at Chemspeed and will be your host today. This is the second webinar in a series of 5, all of them dedicated to the digitalization of R&D and QC labs. This is a new format for us, and instead of talking about our own tools, we want to give a voice to our clients and partners. So in the course of the coming weeks and months, they will describe how they make use of our workflow solutions, how it relates to digitalization, and what it means for the current and future operations. Today, I would like to present a collaboration between Merck, this Merck sharpened dome for the rest of the world, and the University of British Columbia. The scientist and driving force behind this project is Melody Christensen. She's an associate principal scientist at Merck and a PhD student at UBC. Melody, thank you very much for joining us today. I'm very excited to have you here. Actually, it is a very interesting topic we had in preparations of the webinar today, conversation yesterday, and it was planned for 60 minutes. We kept talking for an additional half hour because it was so interesting. So very exciting to have you. And for the start, Melody, please tell us about yourself very quickly and how you came to work in your scientific discipline.
Thank you, Chris. I really enjoyed our conversation yesterday as well. And thanks for the introduction and for inviting me to speak. So I spent the first 5 or so years of my career as a process chemist. And then I was fortunate to have the opportunity to join the automation group in Merck Process Research about 10 years ago. And so it was really there that I found my true passion at the intersection of chemistry and emerging technologies. And my PhD research in the Hein Lab has enabled me to dive even deeper into the development of cutting-edge tools.
Nice. So I read your publication last weekend and was very excited to see how you made use of Chemspeed's technology. And to give us all a brief introduction and to see where you stand in terms of your work, let me put it in the context of our last webinar where we talked to IBM. That was a few weeks ago. And Teodoro Laino from IBM, as well as you both use new technology to basically improve chemical process development. But IBM's focus is on route scouting. This means finding the most efficient synthesis path towards one target molecule. And you, Melody, dedicate your research to the next stage in this value chain of material development. So process development, what you're doing follows route scouting and focuses on the optimization of a single route by varying synthesis parameters like the stoichiometry of the reactants, the temperature, catalyst, etc. And if we want to optimize a process, basically the least elegant way we can do this would be just apply brute force and permutate all of the involved parameters. And as you can probably imagine, that this approach would take up a lot of time, even with a limited set of variables. Such an unstructured approach would probably not be sustainable economically, even for a few parameters, let alone 5 or more. And this is why we develop systematic approaches like, for example, design of experiment or DOE. And the goal of these approaches is to reduce the sampling or the number of experiments to a minimum while, ideally, maintaining the ability to find the best possible result in the entire experimental space. Now, even if you're very clever in designing these experiments, you will be required to carry out hundreds of reactions and analyze their outcome. And this is the challenge we're talking about today and how you, Melody, take advantage of digitalized automation to overcome it. So during the next half hour or so, Melody will give an overview of her project, and then we will have some time to answer questions. So if you're wondering about a thing or two, please type them into the Q&A section on your right, and we're going to answer as many of them as we can at the end. And if you run out of time, we'll get back to you by email. And I look forward to the presentation. Melody, please go ahead.
Okay, great. Thanks again, Chris, and thank you to everybody for tuning in. I'm really excited today to share with you some of the work we've been carrying out in the area of autonomous reaction optimization. So this is a collaboration between the Merck Process Data Rich Experimentation Lab as Chris mentioned, and the High Lab at University of British Columbia. And so before I dive into the research, I think it might be useful to give you a little bit of background for both labs. So the Merck Process Data-Rich Experimentation Lab likes to leverage automation technologies across a variety of scales and a variety of throughputs in order to enable and accelerate process research and development. And this is accomplished through a variety of automation technologies, such as automated high throughput experimentation, automated sampling, automated reactors, as well as process analytical technologies. And really the goal here is to extract as much information from each experiment our process chemists carry out as possible in order to inform the process development and to improve process understanding. And so this actually aligns really well with the goal of the University of British Columbia High Lab. Now, the High Lab is more involved with custom robotics and building custom robotics tools, coupling them with online analytical technologies or process analytical technologies in order to gain deeper understanding and mechanistic understanding around reactions and improve processes. So very nice synergy between the two labs. I've been really lucky to be able to work in both labs, and kind of a natural extension of this work is the development of autonomous process optimization technologies. So I think it's worth taking a few minutes to outline what we mean by autonomous process optimization, right? So we can start at the, excuse me. Okay, so we're going to start here with the scientific method. Okay, so thinking about the scientific method, I'm sure many people who have called in are quite familiar with this, and it involves the hypothesis, experiment, and analysis cycle. And so a lot of pharmaceutical companies have already moved towards automating the experimental execution of their experiments, right? And so, in addition to this, a lot of companies have also begun to adopt online analytical technologies to be able to measure experimental outcomes. And, really finally, if one were interested in trying to develop an autonomous optimization technology, all that's needed is an artificial intelligence technology. And so once these three technologies are integrated, then it's possible to develop a closed loop system that enables autonomous reaction optimization. And this does really take a team of multidisciplinary scientists, right? So I just wanted to point out that, although I have spearheaded this work, that many were involved with the development of this technology. We have Loic and Flo from the University of Toronto, the Asper Guzik group, who developed ChemOS, an autonomous reaction optimization orchestration software, as well as the machine learning algorithms that we used in this work. Toby from the University of Utah, from the Matt Sigmund group, who really helped us define our search space in a systematic way. Lars from the Hein Lab, he integrated the three components in order to generate the closed loop system. And then finally, myself, who spearheaded the automation and the project itself. And so I'll be speaking on behalf of all of us when I speak today. And so why go through all the trouble of developing an autonomous optimization platform, right? And so in my view, there are 4 reasons for that. There are many reasons, but I'll outline 4 here. And the first one is efficiency, right? So if we can enable the automated execution of routine work with minimal human intervention, we can run experiments 24/7. And so that means we're going to hopefully increase efficiency. In addition to this, by automating data flow, we are actually improving quality. We're reducing transcription errors and saving time, and also enabling searchability. I am aware that many pharmaceutical companies are generating much larger data content than they ever have, and it has become difficult to manage this data and search through this data and access the data in certain instances automating the data flow right from the get-go, right at the start, really enables you to be able to kind of develop those platforms so that searchability just becomes something that extends naturally. And thirdly, costs, right? So the idea is that by running brute force experiments, you're running a lot of unnecessary experiments, right? But if you incorporate artificial intelligence and machine learning tools into your experimentation workflows, then you will be minimizing material and time requirements by reducing unnecessary experiments. And then finally, it's a new capability, right? So design of experiments, as Chris mentioned, was developed as a reaction optimization tool. High throughput experimentation is also a reaction optimization tool. And so I think that algorithmic optimization is just a complementary technology, and we'll find many uses for it. And in our experience, we found that it does facilitate the optimization of complex multivariate reactions, especially those involving combinations of categorical and continuous variables. And so, has this type of workflow been developed before? And the answer is absolutely yes. In fact, some of my heroes, the Jensen group, the Jameson group, Stephen Lay, they've all worked on developing autonomous optimization workflows for process optimization specifically. But these all share one thing in common that I think is not a weakness, but a little bit of a limitation, in that they're all carried out in flow reactors. And so, although this is really pioneering work, not all reactions are amenable to flow, such as heterogeneous reactions or reactions that require impractically long residence times. In addition to this, I've seen that categorical variables are not explored to a deep extent in any of the examples presented by these groups. And so we were interested in being able to explore more categorical variables and to be able to do this in batch. So we thought, can we develop a platform that's accessible, where we could carry out batch experiments using off-the-shelf robotics? And that brings me to the Chemspeed swing robot that was sitting in our lab. And we had been carrying out a large amount of high throughput experimentation reaction optimization studies using this robot already. And so we thought this would be a really, really nice platform to integrate with an artificial intelligence algorithm. And so what we did was we outfitted the Chemspeed robotics platform with an online HPLC valve to enable online analysis of our reaction mixtures. And then we developed a lightweight Python tool that would connect the reaction optimization algorithm with the equipment, as well as the online analytics technology. And so once we established the closed loop, we were, kind of ready to go, and we wanted to validate our platform on a transition metal catalyzed reaction that would be of use or of interest to the process chemistry community. And so we selected a Suzuki cross-coupling reaction, a palladium catalyzed Suzuki cross-coupling. And one of the reasons we did this is there's a great review article in OPRD that came out last year on high throughput experimentation, and I've provided the reference below. But there it's outlined that the most highly screened cross-coupling reaction is the Suzuki cross-coupling reaction. And so it is of interest to the pharmaceutical community. In addition to this, this reaction actually did pose a number of challenges, in that there was an unexpected selectivity challenge. So I don't want to scare the non-chemists with this catalytic cycle, but I just want to point out that Suzuki cross-couplings of vinyl tosylates or vinyl halides usually proceed with retention of the olefin bond geometry. And what that means is, if you start with the E-olefin isomer, your cross-coupled product, where a bond is formed between these two carbons, should retain that olefin bond geometry in the absence of background isomerization, which can be driven sometimes by phosphine ligand or base. But in our case, we didn't see any background isomerization. But interestingly, when we screened this reaction, and we've been interested in this reaction for a number of years, in fact, since 2016, we found that out of 23 Buchwald's palladium bio precatalysts screened, that only 11 actually afforded the Z product the unexpected product, and only 3 afforded the expected E product. And that was not really in the best selectivity. Under palladium DPBF catalysis, we observed about 1.6 to 1 E to Z selectivity and only 52% yield of the E product. And so we thought this would be a great optimization challenge because the selectivity was dictated by the choice of ligand. In addition to this, it could also be influenced by a number of other continuous parameters. And so this was the perfect multivariate optimization challenge involving a combination of categorical and continuous parameters. And so we started designing our experiment. And so we decided to start with a palladium precursor and phosphate ligands. This is a 2-hour reaction time. And we decided to explore 5 factors. The first factor being a categorical factor, and we selected 12 representative ligands and also explored 4 continuous variables, including phosphine to palladium ratio, catalyst loading, the equivalence of the aryl boronic acid coupling partner, as well as the reaction temperature. And not only did we configure the algorithm to optimize for maximizing the E product yield, we also configured it to minimize the Z product yield, essentially configuring it for selectivity. But also, as good process chemists, we also configured it to minimize the loading of the catalysts as well as the coupling partner. So we're really asking a lot of this algorithm. And so because we have so many variables, we decided a reasonable number of experiments or iterations for this experiment would be 120. And if we were to carry out 120 2-hour reactions in series, that would be 240 hours of experimental time, 10 days, not very practical. So we decided to optimize in batches of 8. That way we can carry out the optimization in 15 loops. Right? And so then we can complete 120 iteration optimization within a much more reasonable time frame of 2.5 days, and that would be competitive with a high throughput experimentation run. So here are the ligands that we selected. And so we have triaryl phosphines, trialkyl phosphines, dialkyl aryl, dialkyl biaryl, as well as ferricinyl phosphine ligands. And I think those who are familiar with Suzuki cross couplings would probably agree that this is a pretty comprehensive selection of ligands to explore based on chemical intuition. And by chemical intuition, I mean, a combination of literature precedent and field experience, right? And so we thought we had come up with a pretty diverse ligand set here. I'll get into more around that later. And so here, I just wanted to show you a video of the Chemspeed platform. So here you can see the Chemspeed robot deck in action. And yes, those are sparkles, in fact. And so, and then on the right, you can see the different parameters being varied for each experiment and the corresponding assay yield of the desired product. And so a couple of things I wanted to point out are that really this platform ran nonstop for 2.5 days. And so that was with no human intervention. Once the stock solutions are prepared, then the robot takes care of the rest. You can see we have the stock solutions of the various starting materials, as well as the reaction plate. And then towards the back here, you can see the online sampling valve for the HPLC. And so another really interesting feature of this is that that Florian developed a natural language processing capability. And so what this enabled us to do is to control ChemOS through Slack. And that was kind of a nice feature that we really enjoyed. And so before I move into the results of this experiment, I would like to take some time to explain how the optimization algorithm works. And so if you think about the manipulated variables in your optimization experiment, such as phosphine ligand or phosphine to palladium ratio, and then the responding variables such as E product yield, each reaction will have an unknown response curve. And so as measurements are taken within an algorithmic run, then an estimated response curve will be generated. Associated with this estimated response curve will be an uncertainty estimate. And so this uncertainty estimate really has to do with how many measurements have been taken within that area. And so what the algorithm is configured to do is to sample high-performing regions, that's called exploitation, by sampling near expected maxima, but also explore near uncertain regions to gain more information about those regions. And I'd like to thank Ben and Fraser for some really nice graphics that I think clearly exemplify how this algorithm works. And really, this is enabling two things. So the first is that it enables us to not get stuck in a local optimum and to find a global optimum. The second is that you're essentially refining the response surface as you gain more data. So the algorithm is actively learning as you go through iterations in an optimization experiment. And so with that, I'd like to show you the results of the very first optimization run that we carried out. And this is a lot to look at. But this is a really complicated experiment. And, it was kind of one of the interesting things that we found is that how do we visualize what the algorithm did, right? This was the very first time I carried out an experiment where I didn't know what parameters were selected. And so we wanted to understand that and be able to visualize that. So let me walk you through this kind of complex visualization really quickly. So the visualization shows is grouped by ligand, the ligand selected by the algorithm at the top, and then experiment number at the bottom. So you could kind of see what the algorithm kind of went through for each ligand kind of over time. The first row is a bar chart representing the desired product yield. The second row, a bar chart representing the undesired product yield. And then the remaining 4 rows represent the values selected within the ranges provided for each continuous parameter. Color also represents the desired product yield, red indicating a high desired product yield. And so we were really, really pleased to find that we identified conditions that accessed the desired product at 65% yield within this first optimization experiment. So that was really great, but if you remember one of my introduction slides when I laid out the Suzuki cross-coupling reaction, we already knew DPPF was a selective ligand for this reaction. So although this was really nice proof of concept, it wasn't that exciting because we learned something we already knew, right? So we didn't really learn anything. And so we thought, okay, we can do better than this. And when we look at this bar chart, one thing we'll notice is that really it appears that ligand is one of the most important factors that dictates selectivity in this reaction. Many ligands are Z-selective, as you can see. And so we thought, can we approach ligand set selection a bit more systematically? And the answer is yes, but we need to be able to quantitate features around these ligands. And so the Sigma group at University of Utah have been working on this for a long time. So they've actually been mapping the chemical space alongside there are other groups like Natalie Fay who have also been working in this arena, but mapping the chemical space of phospholigands using both electronic descriptors and steric descriptors. So here I show you some examples of electronic descriptors that one can consider with respect to phospholigands. This list is not exhaustive. In fact, there are hundreds. And B-min being an important one, the electrostatic potential, the minimum of electrostatic potential in the phosphorus lone pair region, and also steric descriptors. These kind of will kind of describe the bulkiness, if you will, of a phosphate ligand. The most common being baried volume, as well as sterile. And so what the Sigma group have done is they've used principal component analysis to collapse hundreds of these descriptors for 365 commercially available phosphate ligands into fewer dimensions through principal component analysis, right? And so here you're just looking at all of those ligand parameters with respect to the first 2 principal components. So it's a 2-dimensional visualization, and color represents V-min here, and in this one, volume. So showing electronic as well as steric features. And so what Toby from the Sigma group did for us is he carried out a k-means clustering on the first 4 principal components, so PC is principal component, to generate 24 clusters. And those are represented here by color. And we selected a ligand from each cluster. And we refined our experimental design. So these are the new ligand selections. In fact, we were only able to select 23 because one of the clusters contained ligands that were very, very difficult to access. And they had undesired properties such as high volatility. And so these are what we selected, but you can see that there's some really interesting substitution patterns like silyl groups, polyfluorinated phosphines, not phosphines you would normally consider. I have to say, when I first saw this list, I was a bit taken aback, but kind of went in with an open mind and revised the experimental design a little. Because of the increased number of ligands, we dropped aryl boronic acid equivalence as a factor, and also dropped it as a response, and increased the number of iterations from 120 to 192, and also incorporated 16 standard experiments run under standard conditions to test for reproducibility within our experimental workflow. And I have to say, it was actually really good. Reproducibility was high. And here are the optimization results with that revised ligand set. And so here you can see that one of the ligands, so same type of visualization, is performing really, really well, right? Turns out that is phenyl S-phos. And so within the 161st iteration, we were able to access the desired product in 73% yield and improve the selectivity from 1.5 to 2.5 to 1. And we actually learned quite a lot from this experiment, because we also found that very similar ligands to this, if you substitute these phenyl groups with cyclohexyls, give almost no reactivity. That's shown in ligand 31. And so that's actually S-phos. And so really, we also found that other high-performing ligands were all triaryl phosphine ligands. And so we learned a little bit, and really found that the systematic ligand set selection improved our E-selectivity, right? And we also learned a little bit about the continuous variable. So we were interested in kind of measuring and understanding the influence of phosphine to palladium ratio. So here I show you the same visualization grouped by ligand, but then sorted by phosphine to palladium ratio. So you can see we're going for phenyl S-phos from a very low ratio to a high ratio. And you can see this kind of U-shaped response with respect to the E yield, where at low ratios, you have a decrease in the E yield with a corresponding increase in the Z yield. And then at high ratios, the reaction is shutting down, likely due to closing up of a coordination site. Right, so these are actually expected results, right? I mean, most chemists would probably go with this about a 2-to-1 phosphine to palladium ratio, but not in all cases. And so, you know, it was very interesting that we could kind of infer some understanding around the continuous variables from this data, even though it was very, very, you know, multivariate, and we're varying multiple parameters at a time in each experiment. So it's amazing we can extract trends. And finally, I'm visualizing the same experiment, but just with respect to the continuous parameters that were explored, the 3 explored, and the color again represents the desired product yield. And you can see this kind of red region here, where you are converging on an optimum temperature, about 35 degrees, and optimum palladium loading around 3 mole percent, and then an optimal phosphine to palladium ratio. So you're able to learn a little bit about the trends associated with the continuous variables. And so I just wanted to show you this plot because I think it's kind of interesting. This is, again, color representing the yield of E. So we took each ligand and took the maximum yield of E for each ligand, plotted it against the chemical space map from principal component analysis. This is the old ligand set, and here's the new ligand set. And you can see we've uncovered pockets of high selectivity here. And that was really gratifying. And we thought, we wonder if we could predict additional ligands of high selectivity in this region. And so once again, we turned to modeling, and in this case, regression modeling. And so we're actually, surprisingly, from this multivariate data, able to not only generate a model, but actually take some predictions from that model, scale them up manually, and show the yield. And then kind of here you have the measured yields. This is the log of yield plotted against the predicted yield. And you can see that although the prediction isn't perfect, you are able to predict additional E-selective ligands. And so that was actually quite exciting. In addition to this, we had a control experiment here with the best ligand, phenyl S-phos, and we had actually really good reproducibility when we manually executed this experiment, and that was also gratifying to see. And so although we didn't identify a ligand better than phenyl S-phos, we still thought that it was interesting that we were able to identify additional E-selective ligands and learn more about how selectivity is driven in this reaction. And so I think, that's a good place to stop and just conclude that we've been able to develop this closed loop system for optimization of a Suzuki cross-coupling reaction. And of course, we're interested in applying this to a number of additional multivariate optimization challenges. And through it, I guess one of the learnings that we really had was that systematic categorical parameter selection was key to the success of this particular optimization. And I do believe that in the future, we will find this time and time again. And finally, so just wanted to kind of share again the results of the optimization experiment. And with that, I'd like to move to acknowledge a lot of folks. So my group members, the DRE team at Merck Process Research and Development, Folarin, he was a fantastic collaborator that I worked with that actually developed some of the Chemspeed protocols, as well as our management who have been supporting my PhD work, my advisor, Jason Hine, the Hine Lab for their support, the folks, Alan Asper-Guzik, Florian and Loic at the University of Toronto, and then finally Matt Sigmund and Tobias at the University of Utah. I'd also like to thank the University of British Columbia. I'd like to thank our funding agencies and Chemspeed for inviting me to speak, and then the audience for tuning in. Thank you.
Great, thanks so much, Melody. This is an excellent presentation. I enjoyed that very much, and congratulations on your research and the upcoming publication. Before we move to the Q&A section, there's two questions that came to mind, and I would like to address them first. And one is more practical, I would say. The other one is more of philosophical nature. I will start with the practical one. Coming from the lab myself, being a postdoc for a while, especially in cell biology, I can't help but, so you showed us a very thorough optimization of one reaction with impressive efficiency, but after all, it's one reaction. Clearly, Suzuki Miura reactions are of great importance in the industry, but let's assume, for the sake of argument, that a friend would accuse you of cherry-picking one reaction because that one fits your tools. And I ask these questions because, if you believe that the methodology that you developed is of general significance, then that would maybe encourage some people in our audience to move in that direction, rather than believing that, okay, this worked because you had the right physical chemical parameters of a reaction that just did what it's supposed to in the context of automation or analytics. What would you tell that friend?
That's a very, very good question. And so I will say, and I will admit that we did cherry pick that reaction, but I don't think it's for the reasons that you think. So, or that you would expect. So although it's a Suzuki reaction, it does present a number of unique challenges, right? So first, we don't understand the mechanism of isomerization. So it's not a straightforward Suzuki. Secondly, it's actually a biphasic reaction. So it's not that easy to execute nor sample. It has although it's an acetonitrile water system, which is typically miscible, the aqueous layer due to salt content splits out, and so it's mixing sensitive, which is a challenge. And so there are a few aspects around this reaction that actually don't make them that straightforward. Now, I will say Suzuki reactions are well established, and we didn't want to pick a newer, less established chemistry because this was for validation. And because it's for validation, you want a reaction that has some level of reliability, but that poses enough challenges, such as air sensitivity in this reaction, that you can really kind of test the limits, let's say, of your system. In the future, we are interested in applying this technology to a number of different reaction types involving actually biocatalytic reactions. And so we're excited to be able to share that with you. But for validation, we think this was the appropriate choice. And so I will admit to cherry picking with pride.
Okay, that makes sense. So the second question I have goes into more philosophical depths. And when I read your publication, the way you described the first set of ligands, or the choice of the first set of ligands, you said that this was based on chemical intuition, which is another way of saying, okay, there was a chemist who looked at the ligands, and for some reason, be that just his own intuition or some references that he read about in reviews or publications, thought that these molecules would actually do the trick. And then you show in the second set of ligands that were chosen based on maybe more objective criteria, that you could actually get a better yield. And this conclusion, in conjunction with the entire setup of an automated methodology towards process development, would you say that the results of your publication encourage or would say that chemical intuition to some degree is going to be obsolete?
So, even in our systematic selection of phosphine ligands, we are still focusing on phosphine ligands due to some level of chemical intuition, right? So I don't think that, the craft or the art of the chemists, having this kind of experience, right, is going to go away completely, especially because I think we chatted about this yesterday, and I thought that was a really good conversation, is that, chemistry is built on a set of rules and then also exceptions to those rules. And so it's very difficult for a machine to simulate those, although I think the technology being developed by IBM is getting closer and closer to that reality. However, at the moment, it's not. So perhaps one day chemical intuition will become obsolete, but I don't think it will be anytime soon. However, routine selection of phosphine ligands, for example, why not automate that? Why not make it more systematic? We have the tools, they're being developed. And I think we're going to be very surprised with the results that we see when we utilize these technologies, especially when we're faced with challenges where we have limited mechanistic understanding.
Exactly. And as you say, as you said yesterday, the hard part about arriving at these positive results is that it's hard to come to a conclusion about the mechanistic understanding of it, because at the first instance, there's none, which is very practical on the one hand, but also a little bit unsatisfying at the end of the day.
Oh yes, I could talk about that for a while, because that's one of the things that made made a lot of us uncomfortable with algorithmic optimization data, right? Is that you kind of want to learn what the algorithm learned, but you can't, because it's somewhat of a black box. And so there is a level of there is a level of adjusting as a scientist to that type of thought process.
Exactly, and I think that's a very interesting conclusion. Maybe the right point to start with the first question from the audience. Can we have the first question, please? All right, so Søren asks, can you comment on how scoring functions are best done and told to the machine? For example, in the platinum catalyzed reaction, where 1 subscore is optimized and 3 are minimized. What's the future possibilities for true multi-purpose optimization?
Right. So that is a good question. So we can certainly, so usually the way that this currently is set is we set a threshold for the first criteria, and once that threshold is reached, then the next criteria threshold is met. So you can score, and so you do have the ability to place more weight and importance on more critical outcomes for your reaction. And, in fact, we're not only interested in looking at multivariate responses, such as yield of two products for selectivity, maximize, minimize, but also things like the PMI, the process mass intensity, for example, to measure the greenness of a process, or some measure of the atom economy. We can incorporate many, many different responses into our algorithmic optimizations, thanks to the use of these kind of new and novel Bayesian optimization algorithms.
Okay, next question. Alberto says, 2.5 days of automated experimentation sounds impressive. What is the preparation time to run such an experiment?
Very good question. And I will add that the longest we've gone is 4 days for the 192 iteration reaction experiment. Excuse me. You have to run continuously for 4 days. The preparation time is about a day. Making up stock solutions, preparing the HPLC, carrying out some tests, transfers on the Chemspeed robot. Not too bad. And then you hit go and walk away for 4 days.
Well, it's actually surprisingly little overhead time. So this 1 day, that includes the programming of our system as well as setting up the analytical methods, yes?
Well, the program was written for this, right? So if you were working on a brand new reaction, I would certainly consider, so we did change parameters, so we did have to rewrite once. Yes, of course, that is going to take some time. I think rewriting a program for the Chemspeed using the AutoSuite software of this level of complexity would probably require, for a new project, an additional day of programming and testing. So I would say to get a project off the ground, you would probably need to spend, 3 days or so. If you troubleshoot, maybe up to a week to make sure everything's working well, because these are pretty complicated robotic runs.
But I would assume the longer you do this, the shorter the overhead, especially in proportion to the actual measurement time. Okay, so we already have 5:46 here in Switzerland. We will take one more question, and then we will answer the entire rest by email. Satoshi, what is the most difficult things to execute in an autonomous experiment? For example, which automation part is the most difficult during the reaction, during the analysis and processing the analytical data, or selecting efficient optimization algorithms?
Oh, these are such good questions. It is undoubtedly where we ran into the most problem was the acquisition of analytical data and the processing, the auto processing of analytical data. And so the way this works is that the Python script that we've developed will kind of collect from a text file generated by the ChemStation software peak areas, right? And then calculate yields with respect to an internal standard peak area. And so we found that we were essentially telling the Python script what the retention time of the peak was, but of course you see peak drift, and we had a window for peaks, but there were some close eluding peaks that sometimes would be missed. And I would say that was the biggest headache in this autonomous workflow, and it could be certainly improved by using relative retention time data for peak picking. And I think it can be improved significantly by including mass data as well. But in our particular workflow, that was the biggest pain point.
Okay, Melody, thank you so much for this great introduction to your research, and all the best for your next career steps. This was the second webinar in our series about digitalization in R&D and QC labs. Our next event will be dedicated to how automation enables a more intuitive approach to R&D, called Beyond AI, Gamification of R&D Synthesis. The guest will still be announced. For more information, please stay tuned and have a look at our homepage. Thank you all for your attendance. Thank you again, Melody, and we see you in the next one.